Hello everyone, welcome to my presentation. I am Le-Tuan. Today, I am presenting our research paper titled A Compact Microstrip Patch Antenna with Low Cross-Polarization Radiation for Portable Devices. This research was conducted collaboratively by our team across Phenica, University, Vietnam and University of Galway, Ireland. The focus of this work is the development of a highly compact quarter-wavelength microstrip antenna structure that achieves exceptional suppression of cross-polarization radiation levels. This is a critical requirement for maintaining signal purity in space-constrained wireless applications. This presentation is structured to guide you systematically through our research findings. I will begin with the initial introduction and motivation behind miniaturizing microstrip patch elements for portable systems. Next, I will outline the existing technical challenges, followed by a critical baseline analysis of conventional quarter wavelength designs. I will then present our proposed segmented patch architecture, explain its underlying slow-wave operational principles using an equivalent circuit model, and analyze the resulting simulation parameters. Finally, I will conclude with a summary of our design's verified performance improvements. To contextualize this work, let us look at the primary drivers behind modern antenna miniaturization and why standard solutions fall short. The rapid advancement and commercial scaling of modern portable wireless devices necessitate a continuous reduction in the physical size of internal electronic components. Microstrip patch antennas remain highly favored for these architectures because they present a low profile, are lightweight, and support simple, direct fabrication onto planar radio frequency front-end circuit boards. However, when a standard patch antenna operates at its fundamental TM1 mode, its resonant length is determined by a half-wavelength requirement, making the physical dimensions far too large for modern space-constrained devices. Given these size constraints, various techniques have been established to reduce the physical footprint of these antennas, though they introduce distinct trade-offs. To overcome size limitations, designers often employ specialized techniques such as high permittivity materials, irregular ground plane geometries, or fractal edges. While these methods successfully reduce the antenna size, they frequently introduce severe manufacturing complexities, elevated profiles, or high manufacturing costs. Alternatively, shorting one edge of a patch antenna to ground reduces the required resonant length by half, effectively creating a quarter wavelength antenna. Unfortunately, a major operational drawback of this conventional shorted patch is its high cross-polarization radiation level, which degrades overall wireless system isolation. To better understand this limitation, we must first analyze the geometric structure and radiation performance of a baseline conventional shorted design. To establish a reference point for our study, we modeled a conventional quarter wavelength patch antenna. This baseline antenna is implemented on a taconic RF35 substrate featuring a dielectric constant of 3.5. By terminating one of the radiating edges with a linear row of metallic shorting pins, the standard resonant length is cut in half, forcing the device to operate in the localized TM10, TM20 mode. The optimized baseline parameters for this reference structure were established with a patch length of 9 mm, a width of 7 mm, and a ground plane width of 30 mm. While this baseline configuration fulfills the physical size reduction criteria, an evaluation of its simulated radiation characteristics reveals a major flaw. Simulation results for this conventional shorted patch design demonstrate acceptable impedance matching performance, showing a clear reflection coefficient dip of -20 decibels at the target 4.5 GHz operational frequency. However, its radiation pattern exhibits a severe deficiency. In the principal H-plane, the cross-polarization radiation level rises exponentially to an unacceptable peak of approximately 7.7 decibels. This poor performance is directly caused by the asymmetrical distribution of equivalent magnetic currents along the patch's resonant length, which do not properly cancel each other out in the far field. To correct this polarization asymmetry without increasing the physical size or structural profile, we developed a modified segmented patch architecture. Our proposed antenna resolves this cross-polarization problem through a novel geometric reconfiguration. The design originates from a standard half-wavelength patch structure. For miniaturization and pattern control, we slice the main radiating element into multiple smaller, separate rectangular segments and systematically tie specific zones to the ground plane using shorting vias. This segmentation radically alters the conventional equivalent magnetic current paths. Consequently, it forces strong localized electric fields to form across the small etched gaps between adjacent metal segments, yielding high structural capacitive loading. Let us examine the exact optimized physical dimensions and parametric boundaries required to implement this proposed configuration. The final physical geometry of our optimized radiating patch is square, with outer dimensions of 9.8 mm by 9.8 mm. In terms of electrical size, this translates to a very compact footprint of just 0.28 lambda effective by 0.28 lambda effective at the 4.5 GHz design frequency. The critical internal gaps between the segmented sections are tightly controlled, with a longitudinal gap width G of 0.14 mm and a transverse slot width S of 0.2 mm. The uniform vertical copper strips are set to precise widths of 1.8 and 1.86 mm. The specific layout of these segmented strips and capacitive gaps behaves precisely in accordance with slow-wave transmission line theory. To validate the physical mechanism enabling this size reduction, we can analyze the structure using a loaded transmission line model. The etched physical gaps between the copper segments behave as a network of lumped series capacitors, labeled here from C1 through C8. According to microwave circuit theory, introducing these periodic capacitive loads directly scales up the effective propagation constant of the transmission line. This phenomenon creates a slow-wave amplification effect, which significantly lowers the antenna's fundamental resonant frequency while keeping its physical envelope completely unchanged. Because this slow-wave effect is governed entirely by this capacitive network, the width of the etched gap becomes our primary tuning mechanism. The parametric sensitivity analysis proves that the longitudinal gap width G is the most critical parameter for tuning the antenna. When the gap width is reduced from 0.17 mm down to 0.11 mm, the simulated reflection coefficient dip shifts linearly toward lower frequency bands. This occurs because narrowing the physical spacing directly increases the localized capacitance across the junctions. By selecting an optimized gap value of exactly 0.14 mm, we position the input impedance match perfectly at our target operating frequency of 4.5 GHz. With the optimal gap parameter locked at 0.14 mm, we can evaluate the full impedance and gain performance across the operational band. The simulated reflection coefficient and broadside gain profiles confirm excellent performance metrics at the target operational frequency. The proposed design displays a strong impedance match over a specialized narrow operating bandwidth of 1.2%. Within this defined band, the antenna's realized gain remains consistently high, never dropping below 4.8 dBi. At the exact center frequency of 4.5 GHz, the structure achieves its peak broadside realized gain of 5.3 dBi, which is highly efficient for an element of this electrical size. Beyond impedance matching, the most remarkable achievement of this segmented design lies in its modified far-field radiation patterns. When analyzing the 2D far-field radiation patterns at 4.5 GHz, the antenna demonstrates highly symmetrical broadside characteristics. The half-power beamwidth extends exceptionally wide, covering approximately 100 degrees in both the principal E-plane and H-plane. Most notably, the cross-polarization radiation levels are successfully driven down below -45 decibels in both planes. This suppression represents an extraordinary leap in signal purity compared to the highly problematic -7.7 decibel cross-polarization level seen in the conventional shorted reference patch. To visually confirm the physical cause behind this extreme polarization suppression, we must observe the electric field distribution directly on the patch surface. This simulated surface electric field contour distribution on the radiating patch element at 4.5 GHz offers clear visual proof of our design principle. As shown by the intense color gradients, the electric fields are highly concentrated within the narrow longitudinal and transverse etched gap paths. This strong field clustering definitively confirms the presence of tight capacitive coupling between the adjacent copper segments. It is precisely this uniform capacitive distribution that slows down the wave propagation and restructures the currents to eliminate the unwanted cross-polarized radiation fields. This visual distribution confirms our theoretical circuit analysis, bringing us to the final conclusions of this research paper. In conclusion, this research presents a novel and highly effective method for miniaturizing a quarter wavelength microstrip patch antenna while solving its traditional cross-polarization defects. By introducing segmented gaps and shorting pins, we successfully leverage a localized slow wave effect driven by series capacitive loading. This allows the antenna to maintain an extremely compact footprint of 0.28 lambda effective square while providing a stable broadside gain of 5.3 dBi and achieving an unprecedented cross-polarization suppression level below -45 decibels. This makes the design uniquely suited for modern, high-density portable wireless applications. Thank you, and I welcome any questions.